What's going on, everybody? Zach from MAPerformance coming to you from our shop Evo X for one very specific reason. We are building our engine for this car. Why don't you have a seat, sit back, relax, and enjoy. If anybody knows how to build an Evo engine, it's Aric. He's put together hundreds of these in many different configurations, and over the years has gained invaluable knowledge of nuances and specific ins and outs of the Evo engine program. He's a master of the process, and you're about to see him do what he does best in extreme detail. If you want to see what it takes to make a legitimate 1000 plus horsepower Evo engine, you're in the right place. First up on the to-do list is initial unpacking, cleaning, and verifying of all materials that we're going to use for the build.
Everybody's got their own way of doing it. I just do the way that works well for me. With, you want to wash off all of the kind of like the packaging oil that ARP has on their fasteners. It's not really meant to be left on. We're using ARP 2000 main studs, 625 head studs for this build. And it's really important that you use the fasteners that you're going to run on the engine, because you want to get a couple torque cycles in, and it's called burnishing the threads. It makes the contact point between the nut and the stud stronger than the very first time you use it. So like the main studs will get torqued at least 2 or 3 times, and same with the head studs before the engine's actually ever fired. So going through and doing kind of like this double check before we actually install anything is fairly important. You should only be using what the engine's going to be running with, motor oil, and then the ARP lube. That should be the only things that touch these things. So before we hone it, we want to make sure that everything's kind of torqued up and simulated how the engine's going to be when it's running. That way you get the most precise machining. So torque up these main studs, and that will help us be ready for the line hone after we're done with the cylinder hone. And then we'll get the MAP torque plate put on, and we'll torque the head studs on. And you want to try to get it as similar. It's impossible to be perfect, like versus the cylinder head being bolted on, but you want to simulate the cylinder head being on the engine for sizing the cylinders appropriately. Because once I torque the torque plate on, the cylinders are going to deflect, and I'll show you when we get to that point. And the same thing happens when you take the torque plate off, the cylinders will deflect. And what we're trying to achieve is the closest deflection to resembling the cylinder head being on the engine.
Can't remember if it said or if I looked, and haven't asked anybody. What would you say this engine might be rated for power-wise?
I've seen 1200.
Have you really?
Yeah, but that's O-ringed head, 625 head studs.
Sure.
OEM gasket. Now, you can only use an OEM gasket in standard bore up to like 20 over. So like this is sleeved and it can go up to 91 mil. You can't use an OEM head gasket on that.
So OEM's what, like 86?
The OEM head gasket is 87 mil.
87.
But you need to have, you don't want the gasket to be right on the cylinder. Otherwise that flame front will just torch the gasket. And these are about the best head studs that you can put into this engine. Standard practice where ARP 2000 head studs, I generally rate for under 650. They don't have the tensile strength to hold the extreme cylinder pressures that boosted applications are designed for. Versus 625s, they torque higher tensile strength. They are more expensive, but it's like replacing an oil pump. You know, you think of that as like the heart of your engine. Like if you skimp out on fasteners, you're gonna not have the best results. And what we've always tried to achieve for was the best results using the best parts that were readily available that any consumer can get. You know, there's nothing really custom about this engine configuration. Like, I could make this engine configuration for any of MAP's customers. We've done it a dozen times, and like, the most repeatable results use the best products. That's what we've always done. And then for the MAP Stage 2 Evo 10, this uses an LA sleeve, open deck design. I have the sleeves set up just a tiny bit higher than where the aluminum is sitting, to kind of like double down on the cylinder head sealing. It's called step decking. It helps with cylinder head clamp load, and then also when you start running 30 plus pounds of boost, you don't want the head gasket to be sitting totally flush, because the aluminum block will distort and move around where the sleeves won't. So you want to keep the sleeves proud to help mitigate any sort of distortion that happens. So from here, we're going to put the torque plate on, which is right behind you. So we'll go in here. You can see all of MAP's torque plates. There we go. When we're doing just short blocks, I use my own set of 625s, but since we're going to be taking this all the way and we have your head studs, we're going to be using your head studs for the honing process. So this is the MAP 4B11 torque plate kit. It comes with these standoffs and this plate. There's a lot of them that I use for the engines that we build, but I've used this plate probably 500 times, which is crazy to think about sometimes.
Yeah.
So we'll do our super clean head stud washers, and then we'll lube up the threads, get the nuts on, and then we'll get it loaded into our roller. So I find the smallest one and the biggest one, and make sure that first it's within a range that I'm comfortable with for using all the same size ring pack, setting the same size piston to wall. So the Wiseco pistons that we're using right now, I'm getting half of a tenth of a thousandth of an inch of difference. So very, very minuscule. So we're gonna take our middle spec range, which is 3.3825 in inches, and then based off of what Wiseco wants for the minimum clearance, I'm going to use my own discretion on what we set the piston to wall to, because it's a sleeve block, and the idea of it is to make more power than factory. I add additional clearance so that it's looser in the cylinder, but it can handle more boost without the potential of the piston rubbing or the rings binding. So for this engine, we're going to set it up at 4 thou piston to wall, and that's what we'll set our dial bore gauge at for desired finish size. So 3.3865, and Wiseco's recommendation on their supplied piston sheet is 3.386. So it's half a thou bigger than what Wiseco wants, and they're recommending 3.5 piston to wall. So my measurements and Wiseco measurements are identical, which is good for repeatability. You know, we know these ring packs will work good. We know that the pistons are all manufactured the right way. So we'll roll this forward to 3.3865. So I'm zeroing the gauge. to the final bore size, and then we'll go check it with the block and see how much more we got to go. So 7th out of hone, we took 1. So now I'll have it take 3 more thou out, let it cool down a little bit, and we'll keep going up until we approach final size, where we switch into our finishing work, where we run 3 different setups. We'll run a roughing to get the valleys of the crosshatch right. We'll run a finisher to get the smoothness right, and then we'll brush it to make sure that it's the right finish consistency. That'll just run, and we're going to start working on the cylinder head next. So for this CNC ported head, we're going to be using Ferreira valves and GSC valve train components. So first step to this is we're going to grind these valves, make sure that they're all true and that it has a perfect sealing angle. And then we'll go through, size the guides, cut the seats, and then we'll get it resurfaced and shimmed to the GSC billet S2 cams, and then assembly. So this is a really common combination for MAP head builds: Ferreira valves, GSC springs, GSC cams. For the new GSC cams, we're going to be using brand new valve tappets, and then we'll be using GSC valve seals as well, and all brand new cam bearings, and we'll pair all of that up with our short block and put this into a long block configuration for you, because they're brand new, but also if I don't touch it up, I don't know how perfect that angle is. That's why it's important to not just take stuff off the shelf and put it into your engine, but have somebody that's really good with engine work verify and qualify all of these parts. Yeah, so now that the bores have been roughed in, and then we just ran our finisher stone, we'll run our plateau brushes, and that kind of sets the cylinder wall to accept a new ring pack and kind of start fresh with it being a standard bore block. You could technically do this process on a MAP stage 2 all the way up to 90 mil. So you can rebuild this 8 times. You could do this 8 times over and over and over, which is kind of the advantage of sleeving an Evo 10 versus running the stock sleeves. So we'll send this down. This will knock off any of the rough peaks and kind of set the final surface finish that I'm looking for. And we'll check it with a tester to make sure it's the right finish before we take it out. So, you know how this is set to our finish size. Checking our bore. You want to be right at that 0 mark. So this machine is super repeatable when it comes to getting the cylinder size appropriately. I'd say, you know, it's about this done about 800 to 900 blocks for MAP with this process. So we're really kind of strict about how we hone blocks. Same with line honing, because that's all the finesse work. You know, the resurfacing, that's a really simple process. You're just cutting one plane. Where this, you know, you're making sure you have 4 cylinders that are perfectly straight, that are all the size that you want them to be. And that's the same way with an align hone. You know, you have 5 journals that you're trying to make all the same size in one shot. So. once this is done, we'll check our surface finish, and if it passes the tests that the specs that I want it to be at, we'll take the torque plate off, we'll deburr the top of the sleeve, and then we're going to take it out of here, and we'll go right into the line home. This shows me the highs and lows and how linear it is. And there's a certain range. It's not an exact science. You want it to be within a spec that you determine to be successful. So this is showing that I have 47 for valleys. I like to be within 40 to 60. I like to be within 18 to 22 on the RA. I like to be within 140 to 160 on the RZ, and between 8 and 15 for the peaks. So it's perfect. It's pretty much simple addition, subtraction. This measures this thick, this measures this big, this measures this big. That gives you a ballpark of what your bearing clearance will be. So we'll take our overall size of the main bore compared to what we measure off the crank and how thick our bearing shells are, and that kind of tells me what number I should be leaning towards. And then I can always compensate by running slightly thinner, slightly thicker bearings, as long as this dimension retains the factory spec.
So it's very uncommon to get a one pass line hone.
It's very uncommon. It just means that, like, well, so the other thing is, if you're using a line hone, it's for two reasons. You had something happen to the block, and now your main bore is distorted, and you're trying to correct it. Or you're putting in upgraded fasteners that change the dimension because they're not torqued the same as the factory hardware was, and that changes the sizing of stuff. So that's the process for machining a stage 2 for the most part. And then, like I said, this engine can go 10 over, 20 over, 40 over, 60 over. Like, it can be rebuilt multiple times, which is...
It's really nice.
Yeah, it's a nice advantage of having a sleeve block versus a factory sleeve. So we'll get this loaded up in the parts washer, and we'll let it run, and we're going to start on that.
With the block perfectly honed, it was time to move on to prepping the cylinder head for assembly. Aric began the machining process for the head itself, which is a very precise and intricate process of removing material from the head, paired with an initial test fit and verification of the cams, and finally, sizing and clearancing of the valve train components.
So we're going to be setting our valve clearance today. We'll want to shoot on the high side of the clearance, because as the valve train breaks in, the clearance is going to tighten up a little bit. So you always want to shoot on the higher side than the tighter side, because if it's looser, you're going to be the only one that knows. If it's tighter, you're going to run into early valve train wear issues. And realistically, tighter is not better in a race engine per se on most applications. So for this one, it wants 7 thou to 9 thou. For the intake camshaft, we're going to be shooting closer to 9. Exhaust, they want 11 to 13. We're going to be shooting closer to 13. So we're going to get that set. And then just a quick note, these cams, you have to run an aftermarket valve spring. We're going to be using the GSC 5042s, really common pairing with the billet camshafts. And then it also says to check the cylinder head clearance for the lobes. Some camshafts can make contact with the casting of the cylinder head itself. Every head is cast slightly different, so you always want to double check that you're not going to make contact anywhere, because like I said, the cylinder head will expand as it's running. So we already checked our clearance on that, so we're ready to start our valve shimming for our billet camshafts. We're shooting for 9. Nice. 9. Can't put a 10 in, but a 9 is a nice snug fit. We'll just go down the line and get them all as close together as possible. So this one's at a 7, so I'm just going to dust a little bit off of this. So now that we got this dialed in and we verified that it's level to the cutter head, I'm going to go through and deburr all the sharp edges and then countersink all the head bolt holes, and that'll give us a smooth finish after we take our cut so that there's no sharp edges anywhere for the final product. So, factory crankshafts are factory balanced. They have an acceptable range from Mitsubishi. We take it a step further and we try to get them under a gram is desirable for race applications. Same thing with like the rods and everything. They're all weight matched. We're going to be using Wiseco pistons with Manley rods and King bearings for this crankshaft. Really common MAP Stage 2 parts. When you order the Stage 2 from MAPerformance, you get this crank with the Turbo Tough rods, the HD Wiseco pistons, and then we'll run the coated bearings, and then all of it will be weight matched to under a gram of all of the components themselves. This crank being an inline will be balanced on its own versus like a V8, which you would have to simulate the weight of the rods and the pistons being on the crank. But since this is a inline and you have 2 up and 2 down, we can balance this statically by itself. 2 and some change and 2. So it wants me to remove. So we're going to drill a hole right here and right here, and we'll lower that out of balance factor down to ideally under 1 gram. So it's not bad, but it's not good enough for my standards. So we'll mark 2 holes. It wants weight taken out of identical spots, so it's just a tiny bit heavy on right here. So we'll make holes that look like this, not quite as deep though, and then we'll deburr all these holes to help kind of like prevent any excessive windage or oil splashing. So get the drill bit out and start drilling. We'll get this thing measured up, and then I'll spec out what bearings I want to start with, and then we'll go either first try on the bearings for clearances, or we'll play around with what selection I want to put in for the final install. To know your bearing clearance, you need to know what this diameter is. Some people use Plastigauge. I use physical bore gauges that were measuring the difference of what this diameter is to the housing bore with bearings installed into the block or into the rods. So with this just being measured and it passes in factory spec, we're going to start off with using the standard bearing, and we'll check our clearance, and if the clearance is too large, we'll be switching to a half of a set of slightly thicker bearings to kind of make up that bearing clearance, potentially on the main and the rods, depending on what our physical measurements tell us. So we're going to get set up on that, and then we'll start the short block assembly from there. So I'm getting the block set up to check main bearing clearance. So we're going to install the main studs and the main bearings and the caps. We'll torque it all on, and then we're going to use our micrometers and our bore gauges to get actual clearance measurements and figure out if it's where we want it to be, or if we want to pivot to a different bearing that yields a better bearing clearance. Normally with the aluminum blocks and how much they grow when they heat up, you want to set these ones a tad bit tighter than per se an iron block. So with this, we followed the 1 thou clearance per 1 inch diameter. So this is a 2.2 inch journal. So minimum clearance that we'd want to see is about 2 thou 2/10. Acceptable range for race applications is a hair looser. So if it ends up around 2.5, that's fine too. But on a block like this, you wouldn't want like 3 thou main bearing clearance cold, because that could be upwards of 4.5 to 5 thou main bearing clearance when it's running, and the bleed off from the bearings in the crankshaft can significantly lower your oil pressure. So the game with building an engine for a race application is that kind of sweet harmony where it's not too tight and it's not too loose, so that you get good oil pressure throughout the engine and not just at the crankshaft. So now that we have our main caps torqued on, we're going to set up our micrometer to what we got off of our crank measurements and set our bore gauge and check our clearance. So for this engine, we're going to set it to 2.0463, which is kind of in the middle spec of what a factory crank should be measuring. Just recording what I'm getting for clearancing, that we're going to transfer over to the blueprint sheet. So with the measurements that I'm getting, we're ending up with 2 thou 4/10, 2 thou 4/10, 2 thou 5, 2 thou 5, 2 thou 5, 2 thou 5, and just a hair loose at the very edge with 2 thou 7/10. Totally fine for my professional recommendations. So we'll run these standard bearings, and there's no need to mix match. Now, if we're getting larger than 2.6, 2.7, you know, into the 2.8s, 2.9s, 3s, I would recommend replacing the main cap side bearing with a slightly thicker bearing. And how we do that is King Bearing offers multiple different variants of their standard bearing. So a slightly thicker bearing is called a .026, which is 1/1000th of an inch thicker of a bearing. And then they offer a standard X variant, which is a 1 thou thinner bearing, which would yield a larger clearance. But since we don't have to mix and match, we're just going to rock the standards, and then we'll go do the same practice with checking clearances for the connecting rods. Okay, so now that we have the crank installed into the block, we're going to move on to the rotating assembly. We'll start with checking the small end of the connecting rod compared to what I measure the wrist pin, and then after that we'll check the sizing on the piston pin bore itself. Once those are done, we'll move over to the big side. We'll check our starting housing bore, and then we'll take the rods apart, clean them, install the bearings. We'll get them re-torqued up just like this, and we'll measure the bearing clearance. And if the bearing clearance works in my favor, we'll take them apart, we'll get the pistons hung on the rods, and then we can start filing the rings. And from there, we'll get the piston rod combos put into the short block. We'll modify the oil squirter to make room, because the oil squirter will make contact right here. So we'll bend the squirter in and straighten it out so that it shoots oil up into the top of the piston to help cool. And then once all that's done, we'll install the girdle, and then from there on, we'll do the long block procedure: oil pump, timing, front cover, oil pan, valve cover, and then we'll have a fully dressed engine. So now that we have our pistons and rods all ready to go, the last step before we assemble is to double check or file fit the ring packs. For this, you use a basic equation for what you need your ring gap to really be at the minimum, and then understand like what's too big and what's too tight. So for this, you take your bore diameter, based off of what your piston manufacturer recommends for the multiplication factor. For this engine, we're gonna take our bore size and times it by 0.0055 for the top ring and 6 thou for the second ring. But you wanna double check all of them. You wanna make sure there's no sharp edges on any of the gaps. We'll go through and deburr after we've done our filing. But I start with the expander ring, make sure that there is a gap. You don't really want those to be budding on a forced induction application. So we'll go through and we'll put them all into the bore and make sure that there's no like zero interference fit kind of deal. This one has quite a bit of gap, which is good. We'll go through and we'll just check them all. You don't want to just assume that they're ready to drop in. Just kind of like anything with engine assembly, you should always be test fitting, double checking, validating and qualifying these parts. Now we'll hang our pistons, and I like to put the top compression ring towards the exhaust side because it'll see the most amount of pressure and help it with the initial break-in process. So that goes on like that. We'll put our lower oil control ring on, kind of at the 10 o'clock mark. And then the upper oil control ring on at kind of the 2 o'clock mark. And that's facing the intake side. And then the second compression ring will also be pointing towards the intake side. Like that. And then the top ring will be pointing towards the exhaust side. Like that. And then we'll be using Wiseco's ring compressor to put these pistons in. So we'll set that here. I'll double check where my ring gaps are sitting. Bring it up, over. And then I bring it just before the rings show. And then it's really important on pistons that are directional, where the valve reliefs are different. You want to make sure that you're putting it in the right way. So for this engine, the exhaust is in the rear for an Evo 10. So when you install it, you want to make sure that the smaller valve reliefs are pointing this way. So, and then to install, we'll move the crank down. This will come in. Like so. And then I'll do cylinder 4 as well because of where the crank is positioned. And then from here, this is a common Evo thing that's still running. Piston cooling features with the oil jets that spray up. The jet is bottoming out, or the piston is bottoming out on the jet right now. So if you've ever built an Evo engine and you run Wiseco pistons, you know what I'm talking about, where you have to modify where the oil jet is positioned. What we do for that is we bend the squirter over so that it's coming on the inside of the piston, but without making contact with the connecting rod. So I lock onto it and then I bend it up and over. And I'll do both 1 and 4 at the same time. And you might have to do it multiple times.
After finishing up the modifications to all oil squirters, it was time to get into the meat and potatoes of the full long block assembly process. Aric makes this entire build look easy and simple to follow, and on paper, it may seem that way. But make no mistake, this sort of know-how and precision comes from years and years of perfecting his craft. Watching him assemble this engine from start to finish is truly something to behold.